And now the discussion of lines in space, in 2 space and 3D space. So a line on R2 is the set of points satisfying a linear equation in X and Y. The famous one that you learn in grade school is point slope form. That's if you have X sub naught, Y sub naught, a point on the line, and you have the slope M, and then you can write it as Y minus Y sub naught equal to M times X minus X sub naught. And then slope intercept form, which is the line with slope M and Y intercepts B, is defined to be Y equal to MX plus B. And exceptions, a vertical line has undefined slope and cannot be written in either of these forms, and its equation is X equal to A. So all of these representations were representations that we learned in grade school. Now let's do a new representation. A line in 2 space can be represented by a direction vector. What are we talking about? Let's say line y equal to negative x half plus 5, that's negative 1/2 of x plus 5, has slope negative 1/2, and then when x value changes by 2, the y value changes by negative 1. So you go 2 steps forward, and you incline down by 1 step. And so this means that the line is parallel to the vector v equal to 2 and negative 1. And so that's the direction vector. So we have the direction vector 2 and negative 1, that's v, parallel to the line. Then you start from whatever point or that you want, like basically the anchor point, what would be equivalent to x naught, y naught. And that is the point given to you, 2 and 4. And then from there, you can move in the direction of in a direction of a multiple of v, scalar multiple of v, and you basically scan the entire line, or so this is how it works. That's the P, that's the Q. Q is P plus TV. So it's P as in the position vector P plus R plus T times V. T as a constant. T in here is negative 1. And Q is going to be right there. So another thing that's interesting to know is you can always think of any point as a position vector. And so you add the 2 vectors together and you get the point Q. You get the position vector for point Q. Now, let's change T. For T equal to 0, you get Q to be equal to P, because 0 times V is just 0 vector, and so the position vector for Q is going to be the same as P. Let's change T again, T equal to 1, and you get this point Q, and that's again position vector P plus 1 times V gives you the position vector for Q. And T equal to 2 gives you another one, T equal to 3. So you basically span the entire line. So every line L in R2 we can assign a direction vector to it, v, such that for every p, so for every p and q on L, v is parallel to the vector p and pq. P, Q. That is, there is a scalar t such that pq is equal to t times v. And so in here you can see that vector OP, which is the position vector for P, OP plus PQ, I'm replacing PQ by TV, T times V, is going to be equal to the position vector for Q, which is OQ. And that's what we're using for the to find the equation of the line using the vectors. So the next thing to notice is that for every non-zero multiple of v, you can actually, every non-zero multiple of v is going to be a direction vector for L as well. So if P is a point on L, then the line can be described by the function r of t with a vector r of t equal to the position vector r sub p, that is actually OP, plus t times v. That was what we just discussed. So basically you start at t and then change your position by t times v, and that's how the equation goes. Things to notice, see that when you see that there is a arrow on top of r, means this is a vector. We're talking about vector in R2, so it has two coordinates basically again, and we discussed r sub p is the position vector OP, and that one has two coordinates also. And v is a vector in R2, two coordinates. You multiply it by the scalar t, so you multiply each coordinate by t, and that's a vector. You add up the two vectors. The other thing to notice is that L has many parameterization depending on the choice of p and v. See here we have r sub p and t times v. And so P is the starting point, anchor point, and T is time, and vector V is the velocity. That's something to consider. So you start from a point, and you have a direction to go, which is V, and at every time T, you go more and more in that direction. And so that's another way of remembering this formula. So similarly to a two-dimensional space, lines in three-dimensional space can be parameterized exactly in the same manner as in R2. So in R3, a line is still determined by a point and a direction. So you still have a starting point that in this case is P right here, and you see the position vector r sub p, and then there is a vector that is parallel to the line, that's v, parallel to the line, and what you do is the difference between P and Q is a vector right here, and that vector is going to be a multiple of V. And so if you add up R of P plus that difference vector, you get the blue vector, which is the position vector for Q basically. and see if t is changing, you see you get the different point q. So the position vector changes and takes you to different points on the line, basically. We're continuing with the equation of a line in 3 space. Let L be a line in R3 with direction V. And so the V is a vector with components V sub 1, V sub 2, V sub 3, containing a point P naught, which is X sub naught, Y sub naught, Z sub naught, the 3 components. And so what we learned from previous page was that if R is the position vector for any point on L, R minus R naught, which is the position vector for P, is going to be T times V. And so I can write this down as R of T equal to R naught plus TV, which is, and we know that when we add 2 vectors together, we add them component wise. And so basically what we had in the previous page, it's one way is this, or you can write it as R as a position vector for any point. It's like X, Y, Z, right? And you have R naught plus T times V. And so R naught is just going to be here. This is R naught is equal to X0 or X naught, Y naught, and Z naught as a vector. Position vectors are the same as the point. The coordinates are the same as the point. And then if you add this R naught plus T times that, what is T times V? T times V is, let's change color, T V1, T V2, and T V3. So it's basically multiplied by the components. Now if I add R naught to TV, then it would be component wise X sub naught plus TV1, Y sub naught plus TV2, Z sub naught plus TV3. And so that would be the equation of the line, in the vector format. And then, so what does this say though? It says that the position vector, the first coordinate of the position vector is X sub naught plus TV1. The second coordinate is Y sub naught plus TV2, and then it's Z sub naught plus TV sub 3. And so if you write it that way, if you write X is equal to this, Y is equal to that, and Z is equal to this, then that's the parametric form. Something important to know is that these 2 forms are pretty much the same. You just either write it within a vector form or in a parametric, like each X is equal to Y equal to Z equal to. It's just you're either parameterizing in terms of vectors or parameterizing in terms of coordinates. What happens next is a little different though. So now what we remember from from writing the equation of the line in 2 space, we want to kind of relate X, Y, Z and eliminate T. How do I eliminate T here? Solve for T in each one of these. So this one solving for T gives me X minus X0 divided by V1. Then over here, solving for t gives me t is equal to y minus y0, y naught, divided by v2. And then the last one gives me t equal to, t equal to z minus z sub naught. Z minus z sub naught divided by v3. Oh, t equal to this, t equal to that, t equal to this other one. So what you want to do is you want to set according to t equal to each other. So you will get this, this is equal to this equal to that. So the eliminating t will give you this equation, which is called symmetric equation, symmetric form of the line, basically. And the only what we did over there when we divided by v1, v2, v3, we were considering for non-zero all of them. Otherwise, you cannot. The equation of the line will be missing one piece or another piece of this, basically. Things to notice that this equation, the equation when we eliminated the parameter, is not really one equation. It consists of two different equations. You can say one is that one, and then the other one is, let's say, this one, or any two pairs that you can match, to any two distinct pairs that you can match. Now, the next thing is we just discussed what if one of the coordinates of the position vector is 0. What happens then? And so you will lose one or two of these. So let's say v3 is 0. If v3 is 0, then when you were solving, this term does not exist, and so z is going to be equal to z0, but you will still have this piece. Two of them can be 0. Let's say v3 is 0 and v sub 2 is 0. Then you will have two of your coordinates constants, and then the third coordinate is just varying. That's like a line that is perpendicular to, in this case, xz plane. So these are important points that to see, and we do a few examples. Example 2, find the vector form of the line through point P equal to 2, 3, and 5, and Q equal to 4, 2, and 1. So first part is find at least one direction vector, and the direction vector could be PQ, or could be QP, or could be any multiple of PQ or QP. So first you find, let's say first find PQ, and so that's the vector. Q is the terminal point, P is the initial point, 4 minus 2 is the first coordinate, then it's 2 minus 3, then it's 1 minus 5, and that gives you the PQ, and that could be used as the direction vector. Next, use this direction vector. So this is going to act as our direction vector V. Now, use this direction vector to write out the vector form of the line. So that vector form of the line is going to be R of t equal to, pick whichever point, let's pick P at position vector of P is just 2 and 3 and 5 also. So you write 2, 3, and 5, then plus T times the direction vector that you've found. So position vector of one of the points plus T times the direction vector. Direction vector is just the vector between the 2 points. And now another way, so this is basically 2, 3, I'm doing the arithmetic of the vectors, and T multiplies each component because it's scalar multiplication. And a plus between them, sorry. And now because there's a plus between them, you component wise add 2 plus 2t is the first component, then 3 minus t is the second component, and 5 minus 4t is the last component. So we are emphasizing that PQ is not the only direction vector. There are infinitely many direction vectors and infinitely points on the line. The two that we immediately know are P and Q. We can pick any other point in there and write the equation of the line differently. And so first thing, as you know, there are infinitely many points on the line, and there are infinitely many scalar that can multiply a direction vector and you get another direction vector. For example, I can take this direction vector and multiply it by -1 to get the direction vector -2, 1, and 4, which instantly is going to be the QP rather than PQ. And then from there, with the same process, I will get the line S of t equal to 2 minus 2t and 3 plus t and 5 plus 4t. Now if I switch Q with P, instead of over here I'm using P for these two lines. If I use Q, then I get with QP as the direction vector, we get 4 minus 2t plus 2 plus t and 2 plus t and 1 plus 4t. So you can get a different vector form of the same line. And things to notice is that, so to get the same point out of these two, you can use the same t, so it has to be a different t to get the same point out of them a lot of times. And so that's for instance, in here, if you set t equal to 0, you still get the same point, but other t values, if you plug into R of t or S of t, you won't get the same value. I click your question C. If V is a direction vector of a line L, then -v and 3v are also direction vectors for L. A, true, B, false, C depends on whether V is in R2 or R3. And you can think about it and come back. The answer is true, because if V is a direction vector for line L, then the opposite direction, still a direction vector, is parallel to V, and any scalar multiply of V is still a direction vector. I click your question D. Which of these sets of equations describe the line through points 1, 2, 3, and 2, 2, and 5? So give yourself a little bit of time, find the vector, direction vector, find an equation of the line. So the direction vector, let's say this is P and this is Q. The direction vector is going to be 2 minus 1, 1, 2 minus 2, 0, and 5 minus 3, and that would be 5 minus 3 is 2. So it would be 1, 0, and 2. So that's a direction vector, one of the direction vectors, and you can use any points. From the look of it, A, B, C all use point 1, 2, 3. See, the constant is always 1, 2, 3. Now, the direction vector is the part that multiplies by t. Oh, this is one of those occasions that one of the coordinates of the direction vector is 0. Therefore, that coordinate for the line is constant. That is, y has to be a constant. Y has to be equal to 2. See, it's always 2. So these two both have y equal to 2. This one doesn't, so this part A is out. Then the next part that you notice is that this equation B used that direction vector, but C also used this direction vector, 0, -1, 0, and -2. So both B and C are accepted. E is the answer.